So I wanted to spend a little more time on division because it is the more complicated of the four operations, and I want to see where or how I move between the intuitive side and the purely mathematical side. Or be somewhere in between. But first of all, let's start with small numbers and small examples to just get the intuitive concept of division. So as an example, let's take 2 divided by 1/3. Now, people in general, or before, up to this point, they would think that, oh, I'm dividing, so I get a smaller number. But what does division really mean intuitively? Well, how can I create a word problem where the calculation is, let's say, 30 divided by 5? If you had to make up a word problem for which the calculation corresponds to 30 divided by 5, what could that look like? What could that sound like? How do I understand this intuitively? Yeah, so we make up a word problem. Let's suppose I have 30 pieces of candy, and I'm, let's say, I don't want to use the word divide, we're splitting them up among 5 people. How much or how many pieces of candy does each person get? Then the calculation to find that answer is 30 divided by 5. So my intuitive understanding of division is I have a larger number here, and I'm trying to count how many times does this number fit into the bigger number. Sometimes it's a good idea to make up a word problem because that sort of tells me what the intuitive understanding of a basic calculation is. So now I have the same issue here. I have 2 whole pieces, 2 whole rectangles. And I'm trying to see how many times can I fit in 1/3 into all of this. This is all of what I have. How many times does 1/3 go into this? Well, if I break this up into thirds, I can see it goes in once, twice, 3 times, 4 times, 5 times, 6 times. And therefore the answer is 6. Because I fit in a little 1/3 portion, little area, I can fit that in 6 times. So there's no need to remember, on the intuitive side, there's no need to remember a rule, a pattern, or anything, simply the intuitive understanding of division. And what kind of question am I asking, really? If I have something like 2 divided by 2/3, then the question is, in 2 whole rectangles, that's all what I have, how many times can I fit in 2/3? Well, let's go third again here. Break this up into thirds. But now, let's say to fit one group of 2/3, we need 2 of these little pieces. need two of them. Each one representing a third, and I'm making groups of 2/3. So this will be one group. This will be another one. The gap means nothing. And this will be another one. So I can fit in 2/3 3 times. So it's important to start with the intuitive understanding, because that's how we learn it for the first time. Now, what do I do when the first, well, let's just leave that. So, in general, this suggests a general rule for how to get these answers without a diagram. So what was the other one we had? 2 divided by 1/3 was 6. So a general rule that you can use for when the fractions, for when this number gets bigger and you don't want to draw that many rectangles, or when this fraction is a little unpleasant to work with, I have a calculation like that, some integer divided by a fraction. The rule seems to be, well, I get the same thing if I say 2 times 3. I get the same thing if I say 2 times 3/2. Because this is 1.5. 2 times 1.5 is 3. Now how do I go from 1/3 to 3, which is 3/1? I just flip them around. 2/3 become 3/2. So that suggests that I get the same answer if I multiply by the reciprocal. And that is an alternative way, a way to rewrite the calculation to an easier multiplication. There's definitely a link, just as there was a link between subtraction and addition, there's also a link between multiplication and, sorry, what did I say? There's a link between subtraction and addition, there's also a link between multiplication and division. So now what happens when I take a more complicated first number in my intuitive division calculation? So what if I have 4/5 divided by 1/2? How can I use those rectangles in an intuitive way to help little Timmy figure this out without the rule? Same as before, I don't want to jump to a rule. I want to promote intuitive understanding first. So I definitely start with my rectangle. 4/5, so I'm going to have to split this into fifths as equally as I can, but it doesn't matter. This is what I have. And now I'm trying to see what does a half look like? And I'm trying to fit 1/2. I'm trying to count how many times does a half go into this? How can I make sense of this? The numbers are more difficult now. I'm holding on to that left intuitive side, which means I have to somehow use these rectangles and figure it out. So I understand what division means. I'm trying to count, let's say here. We're trying to count how many times can 1/2 fit into 4/5, or a 4/5 area. So I start with my 4/5 area, and now I have to figure out, how do I look at 1/2? So maybe let's go sideways. And see, excuse me. So now, 4/5, this is what we have. We have 4/5, which is the same as 1, 2, 3, 4, 5, 6, 7, 8. Let's say it like this. 8 of these little, almost squares. That's what we have. That is the area, the quantity we start with. 1/2, I want to fit in 1/2, which half of a whole, right? This is of a whole, which consists of 5 little rectangles. Because I now have the whole rectangle split into 10 pieces. Half of it is 5. So my question really becomes, I have 8 of these little rectangles. I'm fitting in groups of 5. How many times can I do that? So trying to count, how many times can a group of 5 little rectangles fit into a group of 8 little rectangles? I'm trying to hold on to that intuitive method. So I have to try and figure out how these rectangles can help me. So I go, okay, well, 1, 2, 3, 4, 5 there, so that's once. Take a group of 5. Now I only have 3 left, so I can't quite fit in another group of 5. So the answer is, to the question, how many times can I fit in those groups? I can fit in one group, and then what portion of a group do I have left? How much of my group can I fit in? 3 out of the 5 that I need, so 3 fifths. How easy was that on a scale of 1 to 10? 1 being, it's ridiculous, why are you doing this? 10 being, I don't know if I can do this. How easy was that?
I don't know how to scale it, but I'm just thinking of, little Timmy, you're thinking,
Yeah.
split it into 10, but how is he going to think, okay, I'll split it into 10 and that'll work? How do you find the number 10? Do you know what I mean? For him...
Well, it's very similar to what we did before. The first number is split vertically, the second one is split horizontally.
Absolutely, I
So it
understand.
fits with what we did with multiplication. It's this fitting in thing, this fitting concept.
Yeah.
It's definitely much more difficult.
I understand that completely, but I'm just wondering how then does he jump to the number and to think, okay, well if we split this rectangle into 10 pieces, it's going to work.
You have to give him a method, right? But this doesn't require any formula or any rule. And that's why we're on the intuitive side. He still has to have a method, just like the chip model, just like the number line. He still has to have a method of figuring things out.
Yeah.
So the method in this case is vertical split, sideways split, and then fit in groups into other groups. Definitely much more difficult. Much more difficult. Should do one more. I want to do one more. But I don't have an example. I'm going to make up an example. Let's do one more. Because this isn't very as simple as the previous operations were. So let's take, let's go the other way around. Let's go 2/3 divided by maybe a quarter. I want to keep the numbers fairly simple, and there's a lot of little fractions I can have. So now what is this method saying we should do? First of all, I have my number, so I'm splitting it up into thirds, of which I have 2. So the shaded area, that's what I have. That's what I have to work with. I have to fit in, or I have to count how many times can I fit in 1/4 into this. Now I've done the vertical split, and it's not in fourths, it's in thirds, so let's go horizontal to have it just easier. But in doing that, I'm really creating these little rectangles. And I have, and each rectangle is a 1/12 of a whole. So what do I have? My shaded area, I have 1, 2, 3, 4, 5, 6, 7, 8. So I have 2/3, which graphically corresponds to 8 of these little sideways rectangles. I want to fit in 1/4, which is how many little rectangles? It's 1/4 of a whole, so it's 1 of the 4 rows, so it consists of 3 little rectangles. So now I'm trying to look at the groups instead. I have 8 rectangles. I'm fitting in groups of 3. So there's a group of 3. I can fit that in once. There's another group of 3. Doesn't matter how they're lying. Just have to make groups of 3. So I can fit in a group of 3 once more. And now I don't have enough to fit in a whole group of 3. So my answer is, I can fit it in twice, and then a little portion of it still. How much of my group can I still fit in? 2 out of the 3 that I need. 2/3. That is my intuitive side method. But it's not that easy anymore. And these are nice and easy numbers. Not that easy anymore. So just try and pretend these numbers were even slightly more difficult. Sticking to that intuitive side is making me uncomfortable. It's getting a little complicated. What do I do if I have more complicated numbers? And the rectangles in the drawing just falls apart. The numbers are too big and just too complicated. We want to be flexible enough to say, when my intuitive method is, or my intuitive understanding feels like it's lacking a little bit. I'm struggling a little bit to get the answer. I have to look at how do these things actually, mathematical, how do these things actually work? How does division actually work? What is division? And how do I relate it to something that I maybe understand better? Now for that, I find that we should just step away from fractions for a little bit. Let's pause this. Pause. And let's go to modular arithmetic. Because I don't have fractions, I have nice whole numbers and a limited set of numbers as well. It's just nicer to work. So let's take an example. Let's take mod, I don't know. What do I have here as an example? Stick to my notes. 7. 7 is good. Mod 7. So that's an example. So then I have to split this into 7 pieces. It doesn't have to be perfect. 0, 1, 2, 3, 4, 5, 6. Oh, 6 will be over here. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5, 6, and then back at 0. Multiples of 7. So, of course, we've done addition and subtraction, and we've worked with mod any number in the past. So we know that I'm just traveling in a circle, and these are the only numbers I have. So, for example, if I have, 5 times 4, that is what mod 7? Well, 5 times 4 is 20, but there is no 20. So that means if I go once around, I get 7. Another way around, I get 14. To get to 20, I'll be over here at 6. Because 20 can be written as 2 times 7 plus 6. And the remainder is the number I end up with. Does that sound familiar? Yeah. So, addition, subtraction, multiplication is all good. Everything's fine. How do I make sense of division? What do I do with division? Well, if I ask 6 divided by 3, what am I really asking? What am I really asking? So let's say I'm looking for a number here, right? We all know the number. But what does it mean? What does that number mean? Let's say, okay, the number's 32. Mod or not? Because I have 6 things, 6 pieces of candy. I'm splitting it up among 3 people. Each one gets 2. So I can also say 2 times 3 equals 6. Because if each person gets 2 pieces of candy, and I have 3 people, how many pieces of candy did I have in total? Clearly, that's a multiplication problem. So I can rewrite, I can see a division problem as an equivalent multiplication problem by just rephrasing it. So if I'm looking for this number in a more complicated division, I'm looking for, in terms of my example, I have 6 people, I have 6 pieces of candy, splitting it up among 3 people, how many should each person get? If I knew that number, the number of pieces of candy for each person, and I multiply it by the number of people, I'll get the total number of candy. Sorry, that's not a very pretty question. So I can rewrite a division problem to a multiplication problem. And I understand multiplication. So now, for example, let's do 5 divided by 2. Mod 7. So I'm looking for a number on this circle. Division, the intuitive understanding of division now falls apart because there are no fractions. There's nothing like that here. But if I rewrite it to an equivalent multiplication, how does that go? Something times 2 should equal 5. Mod 7. Now what could that something be? While I go through, can it be 1? Can that question mark be the number 1? No, because 1 times 2 is 2, not 5. Can the question mark be 2? No, I need to get a 5. 2 times 3 is 4. 3? 3 times 2 is 6. No, it's not 3. 4? 4 times 2 is 8, which is 1 mod 7. 5? I have to check 5 as well. 5 times 2 is 10, mod 7 is 3. 6? 6 times 2 is 12, mod 7 is 5. So this has to be a 6. Since that's and there's only one number that will work. So we conclude, strangely enough, 5 divided by 2 is 6. Mod 7. It's a little strange, But I'm stepping away from my familiar number line with integers and fractions to look at what division really means. Division is simply a rewritten version of multiplication. where I can rephrase it as a multiplication problem, where I'm missing one of the numbers that I'm multiplying. I'm not looking for the answer, I'm looking for this first one. And by trial and error, I can just find it. So division is really just a multiplication in disguise. All right? Any questions so far? I'm trying to figure out how can I how can I correctly see division when my intuition with the rectangles falls apart. All right, so we have here 5 divided by 2 is 6 mod 7. But 5 times, I just want to make sure I say this right. Okay. 5 times 1 is also going to be 6 mod 7. 5 times 1? No. 5 times 2? No. 5 times 3 is 15. Mod 7 is 1. That's not it. Looking for 6. 5 times 4? 5 times 4 is 20. 20 mod 7 is 6. So 5 times 4 is also 6. What is the link between these guys? So let's just see. What is 2 times 4? And mod 7.
1.
And 4 times 2. Doesn't matter which way I write it down. That's 8, which is 1. So these guys are friends in that when we multiply them together, we get a 1. So we call, or we say, or no, we call 4 the multiplicative inverse of 2. And we sometimes write, just as a name, 2 to the little negative 1 as a superscript. Now see the similarity here between what we did with subtraction and division. With subtraction and division, what am I saying? Subtraction and addition, we looked at additive inverse. Additive inverse. For example, I don't know, 3 with a negative in front means the additive inverse of 3. The number that I add to 3, that would give me a 0. Because 0 was the special number when I add and subtract that it has no effect. But in the multiplication situation, 1 is the special number. That when I multiply by 1, it has no effect. Numbers in the multiplicative sense that together give me this special number, we call inverses as well, but in the multiplicative sense. Addition and multiplication are very different. So I have the same idea, but now for multiplication. So what does this mean? What does this mean? What does this mean? What does this mean? It means that I can see a division problem as a multiplication problem by its multiplicative inverse. The 2 and the 4 are friends. If I'm dividing by 1, I get the same answer if I multiply it by the other. So we say here division by a number is the same as multiplication by its multiplicative inverse. So if I have 5 divided by 2, that is equivalent, the same, it'll give me the same answer when I do 5 times its multiplicative inverse. Those two are going to be the same. Which, then I see, well, the multiplicative inverse of 2 is 4, because 4 times 2 gives me a 1. They're friends. And therefore, 5 times 4 is 20. 20 mod 7 is 6. So, that means that division is simply multiplication by some other number, which in this case we call a multiplicative inverse, by some, let's just say, special friend numbers. That if I'm dividing by 2, its friend in the multiplicative sense is 4, and I can get the same answer if I multiply by 4. So in that sense, just as there was no subtraction, there's no division. It's simply another kind of multiplication. Let's do an example. Still mod 7, but the mod doesn't really matter for us. If I now have 6 divided by 4, division in the modular arithmetic makes no sense in that intuitive setting. Intuitively, I saw division as I have pieces of candy, I'm splitting it up among this many people, how many does each one get? It makes no sense. I have to cross over to a deeper understanding of what this symbol means. It is simply multiplication by 4's friend, multiplicative inverse, which we have established is a 2. So 6 times 2 is 12. 12 mod 7 is 5. There is no division. There is no division. It's just multiplication. Let's do one more. Give me a random number. You're too quiet. Give me a random number. Not too big.
8.
8. Another random number.
5.
Random prime number.
13.
I want it to be...
7. Oh, no.
No, we already did 7.
3.
Sure, sure 3. Sure. I don't want it too big, because too big will give me a lot of choices. 3 might be a little small, but oh well, it's all good. That doesn't really work, right? It needs to be bigger than these guys. So let's go with 13. That was your first choice. I'm not gonna... I shouldn't have argued, I'm sorry. It's my fault. So now, how do I possibly intuitively make sense of that? It makes no sense. It makes no sense. It's a mathematical operation, and that's it. And I have to see it for what it is. It is the same as 8 times the multiplicative inverse of 5. But now I have to go and find out, what is this guy? What is the multiplicative inverse of 5? So if I have my times table, mod 13, and I'm multiplying by 5, I have how many options here? A good number of options, but we'll divide and conquer and find what it could possibly be. Let's do some more here. 8, 9, 10, 11, 12, 0 is 13, but 0 can never give me a 1. So can it be a 1? I'm looking for 5 times something. I'm looking for a 1 here, somewhere. That'll tell me what 5's friend is, 5's multiplicative inverse. So 5 times 1 is 5. 5 times 2, now mod 13, is 10. New. 5 times 5 times 3 is 15. That's 2. New. 5 times 4 is 20. That's a 7. 5 times 5. 25, mod 13. I'm not actually thinking, I'm waiting for you. 12. Starting to worry. Am I going to find it? 5 times 6 is 30. 30 mod 13. 4, because I get 26. And I have 4 left. 5 times 7. Yeah, the numbers get a little big. 5 times 7. 35 mod 13. I can go up to 26 with 13. Nine. Nope, it's not what I'm looking for. 5 times 8 is 40. It's 1. Ding, 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 ding. So that means the multiplicative inverse of 5 is 8 when I'm working mod 13. Which means that this is the same as 8 times 8, which is 64. 64 is what mod 13? Man, I'm asking harder arithmetic questions. 13 dividing into 64? How many 13s can I make? Well, 39 is 3. The next one's going to be 52. And the next one's going to be 65. It's too big. So I can fit in 4 groups of 13. Then I've used 52. And I need another 12. So 12 it is. So 8 divided by 5 is 12. Yes?
Can you just explain why you got 8? How did you know you're looking for the 1?
That is what it means to be a
Right.
multiplicative inverse. They're friends if they multiply together and give me a 1.
Okay, right.
Just like in the additive sense, when they added together and gave me a 0, they were friends. But the 0's role here is played by 1. All right, so now why on earth did I do any of this? Other than to say 8 divided by 5 is 12. Because now I can look a little bit more objectively at my real, my number line. Back to our familiar number line of numbers that we're used to. So now, if I say, for example, what did we say, the example where the rectangle was a little more tricky than we wanted. What was our example that I didn't write down? We made it up. What was it? Doesn't matter. The previous one was 4 over 5 divided by a half. That was the one we did. Now if we have this, we understand that this is the same as multiplying by, I'll write it like this, the multiplicative inverse of 1/2. The role of division and its relationship to multiplication is always the same. So I can always rewrite a division problem to an appropriate multiplication problem, but then the number changes to its friend, its multiplicative inverse. But what is the multiplicative inverse of a half? A I'm looking for its friend so that it gives me 1. What is the friend of 1/2? It's 2, obviously. 2. So this, I'll write over here, is 4/5 times 2, which we can very easily do. Now, we can do this by a rectangle if you want to, or we've done multiplication, that this is 2/1, and you just multiply 4 times 2, 5 times 1 to get 8/5, and write it as a mixed fraction, or whatever you want. But multiplication is much easier than division. And we've done multiplication already. So now if I do an example that's a little more tricky, let's say, let's take the 4/5, it doesn't really matter, divided by 2/3. That is the same because I have a mathematical understanding of division and where it fits into everything. Not intuitive, because I couldn't make intuitive sense of 8 divided by 5 equals 12. It was I moved away from the intuitive side. But now I understand what this actually means. It's multiplication by the multiplicative inverse. Now what is the multiplicative inverse of 2/3? Well, I'm looking for its friend so that they multiply to a 1. What is the number that when I multiply it by 2/3, I get a 1? It'll have to be 3/2. Because in that way, the common factors cancel and give me a 1. So this is then the same as 4/5 times 3/2, which is easier to do. It's a multiplication problem. So I start to notice that the multiplicative inverses are actually now much easier to find. The multiplicative inverses, I cannot write, are actually very easy to find. If I have A/B, its multiplicative inverse is what? Well, A/B as a fraction times 1 is going to be 1. It's always going to be B/A, the reciprocal. So they're very easy to find. I just flip them around. So now my general rule makes much more sense for how to divide by fractions. If I have this doesn't matter, A/B divided by C/D, I can rewrite that as multiplication by the multiplicative inverse of this guy, which is, in this number system, simply the reciprocal. So I had to come up with a rule moving away from the intuitive side so that when the rectangles fail me, I'm able to calculate the answer. But again, it should happen in a much more natural way, that the numbers eventually get bigger, more complicated, and little Timmy's going to struggle with the rectangle up to the point where he asks, isn't there another way to do this? And yes, in fact, there is. But intuitively, where does this come from intuitively? It doesn't really make much sense. I have to be able to step away from the intuitive side, analyze what these things actually mean, and then come back and use it as I need. Any questions or comments? A little bit more complicated than the other operations. I have to be flexible. I have to be able to use the rectangle intuitive method, or as the numbers get more complicated, be able to move away from that comfortably. Let's see what we can do with an example. Oops. And now I'm able to handle many examples. I can have much more complicated situations with fractions where you could ask many things. If you take, let's take a random one. For some reason I like the 4/5 divided by 1.5. Think about that and think how easy is the rectangle intuitive method. You can do it, but it's going to be tough. It's going to be tough. It's going to be really tough. Whew. I don't even want to. Can we even? And the answer might be no. I don't. It's too much work. I don't want to. How do I even work with this? So 4/5 first. 5ths here. Now I could see this as 3/2 if I wanted to. It might make it a little better. 3/2. So I'm going to go split this into two. Sorry, I had 4/5, right? I just shade what I have. Split it sideways according to the denominator in the second number. That was fine. Trying to evaluate now. If I stick to the intuitive side, how quickly do I run into trouble? How quickly does this get complicated? Because I'm limiting myself. So now I have 1, 2, 3, 4, 5, 6, 7, 8. Yeah, let's just say I have 8 of these little rectangles. I'm trying to fit in. How many? How many am I trying to fit in? How many rectangles would be in 1.5? Many, many, many. So, think of the rows, right? For the second number, I'm looking at rows. So I'm taking one row as a half, another row is 1 whole, plus another row, that's 1.5. So it's 3 rows of rectangles. Each row has 1, 2, 3, 4, 5. So I'm fitting in 15 rectangles. The point is that it's not simple at all. That is the point. And very quickly I need something more mathy to rely on, because intuition is only going to get me so far. I'm trying to fit in 15, and clearly 8 is way too small. It's too small, can't do it. So the answer, I can't even fit in 1. How much of my group can I fit in? 8 out of 15. So the answer is 8/15. I know, it's too much. It's done. Like I'm out. That makes no sense whatsoever. That's the point. That is the point. If you stick to the left intuitive side, it's going to give you problems. But we could say here very simply, this is 4 times the multiplicative inverse of 3/2, which is the reciprocal in this system, which is 8/15. And that's nothing. To use this is nothing. To stick to your left intuitive side without an actual mathematical understanding, it can only take you so far. You have to be flexible and move around this spectrum of intuition, intuitive understanding to mathematical understanding as the problem needs it. That is the point of this whole module. So you have to be able to do the rectangle method, but of course also know this. Any questions? That is the end of fractions. well, this little worksheet. Then we'll move over to percentages, and things like that, which we have to know. Percentages, everywhere, there's percentages everywhere.